All right, so let's dive into aldehydes and ketones. So brand new topic. They'll seem familiar, right? We've looked at carbonyl groups, we've mentioned ketones, we've mentioned aldehydes in passing. So let's dive a little bit more into what they're all about. Who are they? So we have two broad classes of compounds that contain a carbonyl group. C double bonded to an O, and then the C is bound to something else is what we broadly call a carbonyl group. And you've been seeing these throughout, right? We've seen this group plenty. We've never really put a name on it in a sense or talked about it in depth, but you've been seeing carbonyl groups all throughout, right? So when we were doing reactions of, we were doing dehydration reactions, right? We were making carbonyl groups. You didn't know it, but we were making carbonyl groups. So compounds that only have C and H atoms bonded to the carbonyl group are aldehydes and ketones. So aldehyde has at least one hydrogen atom bonded to the carbonyl group, which we can see here. So an aldehyde is RCHO. That's how you, sort of the general terminology, RCHO. So anytime you see RCHO, that's always going to be our aldehyde. And then our ketones have two alkyl groups bound to the carbonyl group, which ketones are generally is 2RCO. There's lots of ways to say ketones, but either way, ketones and aldehydes, they have that double bond. So the question of how they differ is aldehydes have hydrogen, whereas ketones do not. And remember, ketones, remember our R groups can refer to really anything that's not hydrogen. So if it's carbon, if it's nitrogen, if it's sulfur, right? Anything that isn't a hydrogen. That's what our R always refers to. Now, many types of our carbonyl groups can actually contain electronegative atoms. So when we have one of our carbonyl groups, so C double bond to the O, R group. Now, if it's attached to a hydroxyl group, so an OH, so one of the R groups is an OH, it becomes a carboxylic acid. This should look familiar if you've seen the structure of proteins. This is what amino acids have in them. They have carboxylic acids. Okay. Then we have esters, which is an oxygen then bound to something else. So it could be like carbon, oxygen, carbon, carbon, oxygen, a halide. It could be anything. But anytime you see this general structure, it's going to be an ester. And then finally, we can have, again, the same general structure, but bound to a nitrogen. That nitrogen can then be bound to hydrogens or bound to something else. And this is what we call an amide group or an amide group. So if you guys wonder why they're called amino acids, the amine comes from this part, amide, because they have nitrogen. As a note. Now, generally speaking, carbonyl atoms is trigonal planar. What does that mean? Well, remember, that's our 120-degree bond angles. I know you guys don't like bond angles, but they're part of chemistry. But trigonal planar, 120 degrees. This means this also has to be 120 degrees. Right? Circle is 360, right? So it has to be 120. Now, you notice that we have carbon and oxygen bound here. Well, as we discussed in lab last week, and we've discussed a few times, when you have a differences in electronegativity, i.e. the electron hungriness of two atoms, we can create a polar bond. So carbon and oxygen, when they bind together, oxygen has much higher electronegativity than oxygen does. Thus, it creates a thus it creates a polar bond. And remember, when we say polar bond, all it is that of these electrons that are shared, right? So there's going to be 4 electrons shared in this double bond. All it means to be polar, it just means the electrons spend slightly more time over here than they do here. That's all. There's nothing funky going on. It's just how often they share. That's really it. So if they had equal sharing, it would be a nonpolar bond, but they have unequal sharing, thus it's a polar bond. And remember, we have the Greek letter, the lowercase d or delta. Minus gives us a partial negative charge on the oxygen, and delta positive gives us a partial positive charge. Again, all because the electrons are simply spending more time here because oxygen's a jerk. Not really, but you get the idea. It just wants to hold on to those electrons much more than carbon does. Carbon's kind of like a cool guy. He doesn't really care. Anyways. So this is what we have. Polar bonds, bond angles of 120 degrees for our carbonyl groups. So let's look at this. So we have acetaldehyde. You guys might recognize acetaldehyde when we talked about the catabolism of alcohol in the human liver a few lectures ago, right? Ethanol is broken down first to acetaldehyde and then eventually to acetic acid. So you might recognize this one. But this is acetaldehyde. Now, CH3CHO, again, that CHO part, pretty commonly showing us we have our carbonyl group. In this case, we have an aldehyde because it's down to one hydrogen and then something else, right? So that makes it an aldehyde, acetaldehyde. Now, we write this such as this, CH3CHO. Now, this might look a little funky because typically we would, I think you guys probably look at this, at least I would kind of look at this. If I saw this, you kind of want to go like this, right? Right? You kind of want to do that, right? Because that's what we don't normally do, right? That's kind of what we do, right? In this class, right? But it's actually not quite that way. Anytime you see that like chew, it's always thinking about it in this context. Oops. H. Just as a note. Not right, correct. I know, it's kind of a weird thing, but just why I'm afraid I make mention of that. And then we have acetone, which is going to be a ketone. Now you'll notice the nomenclature here, the O-N-E. It's a pretty common thing we see with ketones. Very much like, as you guys will learn, like, actually, as I mentioned earlier, right, amines are always nitrogen. Well, ketones are generally O-N-Es. So acetone, which if you've ever painted your nails or seen anyone paint their nails and subsequently remove their nails, well, acetone is a chemical we use to pull off nail polish and things like that. Now, we can write this one of two ways. So we have this, 3D molecular structure, and that's fine. And then we have acetone, which is our ketone. Now, we can write this chemical formula one of two ways. CH3, which is this one. Then we have that central C, and then COCH3. And again, I know the inclination for this sort of thing is to write COCH3 is to kind of go like this, right? But that's not quite right. Based upon that molecular structure, we actually have to draw it a bit different. Just as a note, right? Because this would be a completely different functional group, right? This would be our ester, right? Now, the other way you can write it is like this, CH32CO. Now, I want to just take a special minute here to actually just go over that, because a lot of people had trouble with this on the exam, and I just wanted to make mention of it because it's something it's not gonna go away clearly. So a lot of you guys had trouble with this on your exam. So you would see this thing where it was, I'm writing this right, CH3-2CO. Now on your exam you were seeing things like this, and then you would see like, I don't know, right? Now, important thing here is when we see this subscript 2, the same way if we see CH3, it means there's 3 of whatever the subscript this is on. So in this case, I have 3 hydrogen, right? So I would write that as CH3. Now, here, remember, this is telling me I have 2 methyl groups. So the way I would write this is actually such as this. So a lot of the ways you got tripped on your exams, and I forget what problem it was, I can't remember off the top of my head, but you would see this, and you would make the assumption that this just implied 2 carbons in your chain. So if my chain was 1, 2, 3, 4, you go, oh, 5, 6. So thus I would have hex. But the reality is, when you have this CH3 subscript 2, well, you might go 1, 2, 3, 4, and then you have to choose one of these. Right? So I have to go 1, 2, 3, 4, 5. So it'd actually be hect. And then I'd have to deal with this methyl group 7. Just wanted to make special mention of that today. Because again, I saw a lot of people on your exam get tripped up on it. It's not going to go away. Clearly, it's here. Does everybody feel comfortable with that? If you need a little bit more help, just let me know. But I just wanted to make special mention of that because it popped up here on the slides. And it's like, I probably should talk about that. Again, remember, subscripts in chemistry always means that you have multiple of what the subscript does. So if I have CH3, it just means I have this. Right? And we know carbon only forms 4 bonds, so that has to bond to specific.
Question. That's why you will count like on the sample that you said a heptanol. That's why you only count 1 instead of the 2. Okay, and when you say you should dry like that, like I could put CH3, like the middle group, the 4 carbons, and I could put the other one at the end, or it has to be like that.
Well, it's telling you they're all in the same area, right? So in this case, it's CH3 2 on this specific side. Now, putting the CH3 here is fine, right, as I've done. Now, if I put the other CH3 here versus here, I'd probably get two slightly different molecules. Maybe not, but you should really, like when you're kind of going from this to this, you really want to think about it and keeping them sort of in the same spot. But just remember, if you have any questions on this again, I can certainly go over it again on Wednesday. But I wanted to make special mention of this. So anyways, we can write acetone very much this way, CH3, so central C is here, CH3 refers to this one. So we're seeing 2 CH3s bound to this C, and that C is also bound to an O. And based on what we know about carbon, well, if it's bound to an oxygen and CH3s, it has to have 4 bonds, right? Thus, it has to have a double bond with oxygen. So that's our structure, that's our bonding of our acetones, of acetaldehyde and acetone. So we have to name, right? And I know you guys are probably like, why do we have to name? Naming is boring. Well, I agree. Naming is not the most exciting thing in the world. However, if any of you have any aspirations for medical school, dental school, or veterinary school, you're going to have to take a course called organic chemistry. We don't offer it here because it's a really hard course to staff, but you're going to have to take a course called organic chemistry. And if you think the amount of naming we've done in this class is a lot, wait till you get to organic. So I'm using this as a really great opportunity to make sure you guys are well prepared. So when you go into organic chemistry 1 and organic chemistry 2, you guys are naming champions, just as a note. I know you're like, oh, I'm tired of naming. Well, there's a reason I keep us naming, just as a note. I don't do it just to be mean. I'm not that kind of person. So let's name an aldehyde first. So we're going to use the IUPAC system as always. Now we have to first, as we usually do, find the longest chain. But very much like when we were naming alcohols, that largest chain has to contain the CHO group that defines an aldehyde. Next, we change the E ending of an alkane to an ol. So different from an OL, like an alcohol, we have an ol as in aldehyde. So we have, for instance, if we have heptane, right? All we would, if it was an aldehyde, we'd call it heptanol, AL. Then we number the chain to put the CHO group at carbon number 1, but we omit num1 from the name. So in this case, if I have heptanol, it's a good example. It tells me the AL tells me I have CHO. This tells me I have 7 carbons, right? The CHO should be at carbon number 1. Thus, we don't have to have a name. So like when we have ethanol, right? Ethanol was always assumed the alcohol group was at carbon 1, just as a. And then we just use all the other rules we've been doing thus far. So as with most things, it all started off with the basic rules of naming alkanes, and then we just add some slightly different variations. So let's name these guys. I was going to say bad boys, but that's bad. So IUPAC name of 2 distinct aldehydes here. Let's go. So we find the longest chain. Very straightforward. But the chain has to contain CHO. And what do I mean by CHO? It actually has to contain the C part of the CHO part. So in this case, this one is pretty straightforward, right? It's just a straight line. Right? That's easy. But I think it illustrates nicely here that, well, my longest chain can't go this way, right? This isn't my longest chain, right? 1, 2, 3, 4, 5, 6. That's hexane, cool. But it doesn't contain the CHO. And so I can't go this, right? 1, 2, 3, 4. That contains the CHO, but that's only butane, right? So I'm really left with only one solution. 1, 2, 3, 4, 5. That's the longest chain that contains CHO. Again, if I go this way, I only have a couple options here. Right? I go this way, that's 4. I go the way that's highlighted, which is 5, or I try to do this weird thing, but this weird thing doesn't work because it doesn't contain the CHO. So there's only one way to go here. Now the second one is very similar, right? I'm sorry, the first one, right? Not the second one. But we have 1, 2, 3, 4 carbon, so that's cool. Now we could also go technically 1, 2, 3, 4. If we wanted to. 1, 2, 3, that's too short, right? And 1, 2, 3, 4 doesn't include the CHO. So there's only one way to go here and only one way to go here. But it has to, in that long carbon chain, it has to have the CHO part. Has to. No other way around it. So we know that 4 carbon chain is butane, 5 carbon chain is pentane. Now our rules of naming are aldehydes, we swap E for AL. Butane becomes butanol, pentane becomes pentanol. What does that tell us? Well, it tells us there's a carboxylic acid in this group, or a CHO group, right? Very straightforward. Now, remember, we have to give our CHO the lowest numbers. Now there are, so we're not going to get into these like more advanced naming things, but there are rules like hierarchies of like what has to come first. Like if you count an alcohol group and say a carboxylic group, we're not going to go into that. If you ever take organic chemistry, you'll learn like the hierarchy. But just a note, like I'm not going to give you like these mixed problems like that. So you're not going to you're not going to like note an alcohol and a ketone in the same group. Just as it'll only be one. Just want to let you guys know that. So we have butanol and we have pentanol. Now our first carbon has to be the lowest for this CHO group. So this will be carbon 1. This will be carbon 1 here. So if we go through and label 1, 2, 3, 4, and then 1, 2, 3, 4, 5. How do we finish this name for N? What do we have to address? So we have methyl groups. So I have 1 here and 1 here. So what would I add to my name?
2, 3, dimethyl.
Yeah. So 2, 3 dash dimethyl. Now let's break that down. Bute tells me 4 carbon. All tells me here. 2, 3 at carbon 2, carbon 3. Di tells me there are 2 methyl groups, and methyl group tells me there's CH3. Then we have our next group. What do we have to deal with here? Just one thing. I heard ethyl and ethyl. Yeah. So we have carbon 1, 2. We have 2 dash ethyl, and then pentanol. So similar rules that we've seen. The key difference here, very much like the alcohol, when you're naming alcohols, you got to give that CHO part has to be part of the chain. Has to be. And it finishes the name here, but we already did that together. So for aldehydes. Now, there are common names typically used for simple aldehydes that we commonly see. And they're typically the names containing the suffix. So, formaldehyde, you guys probably recognize, preserves corpses, carcinogenic. Formaldehyde typically looks like CH2O. Acetaldehyde, which we've discussed previously, the byproduct of the breakdown of alcohol in your liver. Then we have benzaldehyde, which is used for actually quite a lot of things. You can Google benzaldehyde and uses. There's a lot of things that benzaldehyde is used for. But again, common names for common things we see. Formaldehyde, acetaldehyde, benzaldehyde. How does it get the benz? The benzene ring. Right? So these are some common names. Now, ketones So our other topic of the day, we find the longest chain containing the carbonyl group. So that should sound familiar. Longest chain containing the group of interest. We change the E to "-one". "-one" signifying the ketone. So if we use our example here, we have heptane. Change heptane. Sorry. Heptanone. That's kind of nice. Then we number the chain to give that carbonyl atom the lowest possible number, like we just did for our aldehydes. And then we apply every other nomenclature rule we've applied thus far in this class. So let's name these two groups. We have this sucker and then this sucker. So I know this looks a little bit intimidating, but it's really not, right? It's just a skeletal structure. We'll be good. So let's start off by getting the longest chain. Now, it has to include that ketone group. So we have here, so we recognize that we have CO, so that implies our carbonyl group. Now we see it's bound to a C and a C, thus it has to be a ketone. Remember when we were looking at aldehydes, remember it was something R, H, right? But ketone, remember, we replace that H with an R, which is what we're seeing here. Remember, R is anything but a hydrogen. So we have to have that longest chain, including our friend, the ketone. So 1, 2, 3, 4, 5, that's great. That's the longest chain in general, but it also includes our ketone. Now we can technically go like 1, 2, 3, 4, but that's a 4-carbon chain. So there's really only one way to make the longest chain here, which is a straight line of 5 carbons. Remember, it has to include that C double bound to O. So we take pentane, because it's 5 carbons, and we change pentane to pentanone. Now let's finish renaming this, or let's finish naming this. So this has to be the lowest number possible. It's not at 1 anymore, right? So in our previous examples, they were at 1. What carbon would you say this is at? How do we name this? Yeah, so we have to give this a low number. So if I went this way, this would be at 4. So I have to go this way. So that's the pent part. Now I have 2 pentanone, tells me it's at carbon 2. And then I have our friend methyl group here at carbon number 3. So 3-methyl. The biggest concern when I'm doing these problems is that I make a mistake. And I go to the next part. I'm always paranoid that I'm going to make a mistake when I'm doing these for you guys. Just like this. So 3-methyl 2-pentanone. Remember the unknown, so this own part tells us there is a ketone. Pent gives us the 5 carbons. The 2 tells us this own part is at carbon 2. And the 3-methyl, as you guys know, there's the methyl group at carbon. Now we have a ring. So we have to use our generalized naming features of our rings. So we can count how many carbons we have. So remember, every time we have a point, 1, 2, 3, 4, 5, 6, that's a carbon. So we have to make sure anytime we have a ring, we have cyclo in front of that ring. I notice on a lot of your problem set 4s, a lot of you guys are forgetting the cyclo parts. Just out of know. So we have cyclohexane. That would be the alkane name of this ring if there was nothing else. But we have that O double bond. Thus, it's a ketone. Thus, we have to change hexane to hexanone. Cyclohexanone is what we have here. Now, remember, we have to give, when we have rings and we have things on the rings, we still have to give the lowest numbers. But as you'll recall from when we were naming alcohols, we got to put the alcohol at number 1. And the same thing here for this ketone. We have to put the ketone at number 1. So this has to be number 1. Ketones are number 1. And then we just use standard naming rules. We just have to give everything else the lowest number. If I go this way, 1, 2, 3, 4. So I'd have 3, 4. And this way it gives me 1, 2, 3. So I'd have 2, 3. I'm sorry, 3/4. Sorry, I can't add. So we're just going to go this way. Either way, it actually doesn't matter. So how do we finish this name off? So we have cyclohexanone, but we have two things. What do we need to add? Ethyl at 3. So we have 3-ethyl. We heard 4-methyl.
And
3-ethyl 4-methyl cyclohexanone. Now, another thing you guys want to make sure you remember, alphabetical order matters here. It has to be ethyl methyl, not methyl ethyl. Even if methyl came after, so if the methyl group was say here, you still have to go methyl methyl, not methyl ethyl. That's a funky thing. 5 times fast. So 3-ethyl 4-methyl cyclohexane, which we got the same answer. Ooh, yeah. So we'll do more naming problems on Wednesday, just so we're feeling good. But again, it should feel like naming alcohol, right? Getting the lowest numbers possible, putting things in alphabetical order, the same IUPAC principles that we've been going for thus far. So ketones can have common names, as most things can, right? Now ketones that have common names are formed by naming both alkyl groups and then arranging them alphabetically and adding the word ketone. So if we name this with an IUPAC name, 1, 2, 3, 4, it would be 2-butanone. Now the common name for here would be ethyl methyl ketone. Why is that? Well, we have the ketone group here. On this side, there's a methyl group. On this side, there's an ethyl group. Thus, ethyl methyl ketone. I'm less concerned about these common names, but I just figured I'd make mention of them. I was waiting in the grocery store line the other day, and I was reading a thing for Tums. I don't remember. I was reading a medicine I was buying, and I was looking at the ingredients list because that's what you do if you forget your phone at home. Why don't you just look at your phone? But I was reading the ingredient list, and I saw not this compound, but I think it was pentyl heptyl ketone. I feel like I should mention it, how you name common, other than common names for ketones, because I saw them on a medicine bottle I bought. Now there are really common and widely used names for things that are really common that we use. Acetone being a ketone. Clearly we don't name it methyl ketone, right? It's just acetone. And then we have a couple other ones, acetophenone and the benzophenone, common chemical things, which functions escape me at the moment, but you can Google them if you're interested, that just have their own specialized. Just figured I'd make mention of them, but you can tell the ONE part, that's ketone. So let's talk about some properties, because this is chemistry and everything has properties. Now, aldehydes and ketones have higher boiling points than similar hydrocarbons. Why is that? Well, first is they're polar, right? They have that oxygen-carbon double bond. That is a polar bond. Anything that has polar bonds like that is, typically speaking, going to have higher boiling points. And the other thing is they're going to have stronger intermolecular forces. And we're thinking about things like hydrogen bonding here, right? This double bond, this oxygen hanging around there, now has the potential to form a hydrogen bond. And things that can form hydrogen bonds typically have higher boiling points than things that have similar structures. So we can give pentane here. So we have our 5-carbon chain. It has a boiling point of 36 degrees. And then we can see butanol, 1, 2, 3, 4 carbons. So we have even one less carbon. But because butanol is a ketone, its boiling point is actually relatively close to water at 76 degrees, whereas the boiling point here of pentane is 36 degrees. So as we increase the size of our ketones, very much like any of our molecules, the boiling point increases. So for instance, butanol has a higher boiling point than, butanol has a higher point than methanol. I know, methanone. Anyways, you get the idea. Larger things have higher boiling points, but when compared to an alkane of similar size, they're going to have higher boiling points and melting points for that matter. Now, aldehydes and ketones have lower boiling points than similar sized alcohols as well. Now, they don't have an OH bond. And so typically speaking, they won't have intermolecular hydrogen bonding. However, you'll notice that this O does leave the capacity open for some hydrogen bonding. And they have weaker intermolecular forces, so they're harder to split apart. So butanone has a lower boiling point than, say, butanol, which is an alcohol. So just as a note. Top of our list is alcohols having the highest boiling. Now, what other properties of our ketones and aldehydes do we have? Well, they're soluble in inorganic solvents. I'm sorry, organic solvents, not in inorganic solvents, but in organic solvents. And typically speaking, those that have 6 or less carbons are typically soluble in water. Again, that CO part here allows hydrogen bonding to form. Not as strongly with alcohol as with alcohols, but it still happens. So because of this hydrogen bonding that can occur, 6 carbon or less ketones and aldehydes are soluble in water. However, those that are larger than 7 carbons are simply insoluble in water. And it's kind of a general property, right? As you increase the number of carbons, it's just simply too hard for water to dissolve those things. The amount of hydrophobicity just increases too much that water, even water itself, is like, I can't handle that. So let's talk about some health and medicine stuff, because I mean, why would we be talking about these if they didn't have some sort of relevance to your everyday life? Now, formaldehyde, CH2O, is the simplest of all the aldehydes, and as I mentioned, it's a really common use thing. So the first, it's actually used as a starting material for the synthesis of resins. So like hard, really like think of like resin as in like things that harden really tough, but they're liquidy until you add something to solidify them. So you think of like almost like a tree sap. It's a type of resin. So they're used for the making of plastics, or formaldehyde, as I should say. And it's also so does formalin, typically has 37% solution for the preservation of biological specimens. Formalin, formaldehyde, whatever you want to call it, it's carcinogenic. So it is, you know, it's not exactly the safest thing in the world, but it's a really great preservative. Why is it a great preservative? It's toxic as all heck to bacteria and to you, for that matter. So really great preservative. We don't use formalin anymore, so when you guys get to dissect stuff, it's not going to be formalin fixed or preserved in formalin. It's going to be preserved in something safer. But when I was in high school, I dissected a fetal pig that was preserved in formalin, and that was bad. Formalin is bad. Now, acetone, as we discussed, is the simplest of all the ketones, CH32, CO. It's an industrial solvent, right? It's used for dissolving things, right? Or getting things to become, you know, essentially like pulling them off of substance, right? So you can think about when you if you ever have clean fingernail polish on your fingernails, you basically makes your fingernail polish soluble, thus pulling it off your fingernails. It's also used as a starting material in many organic polymers. So it does have some industrial applications. Now it's produced in the breakdown of fatty acids in your body. It says no. So there's a pathway. You guys will learn about it when you take cell biology. If you ever want to take cell biology, of course. As you break down fatty acids, you do produce acetone. Now, those people that suffer from diabetes typically have unusually high levels of acetone inside their body, just because people that have diabetic have a bit of metabolic issues as a general note. Now, one of the compounds actually two of the compounds we're going to look at this Wednesday is cinnamaldehyde, which if you guys like cinnamon, which you guys do, cinnamon's awesome. Not that like eat, but the smell of it and the taste it adds. It owes its awesomeness to an aldehyde, cinnamaldehyde. How do we know it's an aldehyde? CHO. Cinnamaldehyde. You guys are going to get to play with this live on Wednesday. It smells awesome. Smells like cinnamon. And then we have vanillin, which is, again, CHO, cyclic ring, so benzene ring here. Now, it's actually the primary component of the extract of vanilla bean. So if you guys have ever made cookies or something, or maybe, like for instance, I make French toast and I put vanilla extract. Well, what gives vanilla extract its nice like scent is vanilla. Now, vanillin, it smells awesome, tastes awful. You guys ever tried pure vanilla? Like just touches your tongue, it's awful. Pure cinnamon, also awful. Smells awesome. Anyways, fun stuff. Now, geraniol, if I'm not mistaken how to spell that, is actually the characteristic odor of lemongrass. So if you guys like lemongrass, which is fantastic, has both a smell and like a flavoring of food. This is its general structure, CHO, so it falls under our O-so-fun category here. It's also used in perfumes, and it's also a precursor for the synthesis of vitamin A in a laboratory setting. So if you ever bought like vitamin A like in a bottle, because your doctor told you or someone, or you've taken a multivitamin, they use geraniol as a precursor to synthesizing vitamin. Then we have citronella. You guys might have heard of citronella before. It smells pretty good. It's not really used as a fragrance, but citronella does have anti-mosquito properties to it. So you burn a citronella candle if you're out in the summer, and it drives away most of the mosquitoes. It's not perfect, but it does a pretty good job. Plus, I think it smells really good. So those are some fun things about ketones and aldehydes. We'll get to see some properties of them in Lab on Wednesday. Now, aldehydes and ketones, they undergo two general types of reactions. Now, we've already talked about this one already, but aldehydes can be oxidized to carboxylic acids. So this is the one we've actually looked at before, right? We looked at acetaldehyde being oxidized fully to carboxylic acid, right? When we talked about the breakdown of alcohol. So that's one that can be oxidized. So remember, O within brackets is going to be oxidation. Now, general rule, remember we generally have that chromium, so that Kr2, something, that long molecule, I forget, it's K2Cr2O7, I think. That's generally our oxidant, just as a refresher. And then we can also see our aldehydes and ketones undergoing addition reactions. So addition reactions should ring a bell from last semester, and it should also ring a bell a little bit from this semester. But what's happening here is we're breaking a bond. So this double bond, which frees up electrons, so that each the carbon and the oxygen can then go on to form one bond. So in this case, our molecule here, ketone or an aldehyde, we sever this bond as it reacts with X bound to Y. So it could be like HCl, for instance. That could be one of the things that reacts here. Thus forming two new bonds, X bonding with carbon, Y binding with oxygen. So, pretty crazy. So typically speaking, when in oxidation, our aldehydes, that CH bond is converted into a carboxylic acid COH bond. So when our aldehydes are oxidized, we're converting the CH bond here into a COH. So we're putting an alcohol group there. However, you'll notice that, well, it's still called a carboxylic acid. I haven't changed it to an alcohol. And why haven't I changed its name to an alcohol? Again, I still have that generalized structure, right? R, C, double bond to O, down to something else, right? Our general structure for a ketone and an aldehyde. So this is what happens when we have an aldehyde being oxidized. Now, ketones cannot be oxidized. They just can't. They don't have that CH bond. So ketones, when they're treated with an oxidant, so in this case, we've represented oxygen with the O in brackets. But remember, if we see K2Cr2O7, that's also called an oxidant. That's what's doing the oxidation reaction. Ketones, they don't have that CH bond here or here. Thus, they cannot be oxidized. But ketones, here a C ketone, cannot be oxidized. Now, aldehydes can also be selectively oxidized in the presence of other functional groups, such as Tollen's reagent. Now, Tollen's reagent we're going to use in lab next week or the week after. At some point this semester, we're going to use Tollen's reagent. I forget when. Now, in this case, we have our aldehyde here. It's bound to a ring, which has an OH group here. However, the only thing that's oxidized is not this ring, but this central carbon here. And very much like we saw previously, it's reacting with some sort of oxidant agent here, only forming that OH here, not touching any other part here. And again, it is selectively oxidized. What does that mean? Well, reality is we're using Tollens reagent, which is a mixture of silver oxide, Ag2O, so that's silver oxide, and ammonium hydroxide, NH4OH. I got that right. And again, it's ignoring every other part. Because remember, we can oxidize this alcohol here if we wanted to, right? That's a thing you can do. But in this case, Tollens reagent actually selectively oxidizes just this aldehyde part here, leaving the rest of this alone, thus forming our OH here and silver. So like pure silver, like elemental silver. So we're going to get to do this in lab later on in the semester. It's not as exciting as it sounds, but you'll get to do it nonetheless. Now, unlike the rest of the things we've talked about, right? We only talked about oxidation thus far, but remember the partner to oxidation is reduction. Right? So oxidation, remember, is the loss of electrons. Reduction is the gain of electrons. So while we looked at alcohols, they simply couldn't be reduced, but they could be oxidized. Our aldehydes and ketones can actually be reduced. So what does this look like? Well, we're decreasing the number of CO bonds, thus increasing the number of CH bonds, which again is the exact opposite of oxidation. Remember, oxidation is we increase the number of CO bonds and decrease the number of CH bonds. So oxidation versus reduction, two different processes, but different sides of the same coin. So in this case, we have our carbonyl group. It's reduced, so we define reduced as H in brackets. And what's happening here is we're basically adding H2. So we're going from CO here, we're breaking that double bond, and essentially just tacking on two hydrogens here. So we have two CO bonds here, then we have one CO bond and one CH bond. Well, technically two CH bonds, but I'm thinking what's bound to the oxygen and the carbon individually. And so we actually form an alcohol. So we can reduce a carbonyl group to an alcohol. Actually, something you're going to do in lab as well. So now aldehydes are reduced to 1 degree or primary alcohols. Why is that a primary alcohol? Well, remember, we define something as a primary alcohol by how many things our carbon is bound to. So it's not how many things the oxygen is bound to, but whatever that oxygen is attached to. In this case, it's attached to this carbon here. How many other different non-hydrogen things is that carbon attached to? In this case, well, it's just one, right? This carbon, where the hydroxyl group is bound to, is only bound to one other R group. Now remember, R refers to anything that's not hydrogen. Thus, this has to be a 1 degree alcohol. Now, you might be asking yourself, and probably not, but I'm asking that for you, is what do we use to reduce any given compound? Typically speaking, we use hydrogen gas and palladium metal, PD, as the commonly used reagent for the reduction of ketones and aldehydes. Now, ketones are, as you might expect, because of their formula, RC double bond OR, they're reduced to 2 degree alcohols. Now remember, what is the 2 degree part referred to? Again, what is the hydroxyl group bound to, this carbon, and how many non-hydrogen things is it bound to? In this case, it's bound to 2 things, right? Remember, R always means anything but hydrogens. So in this case, we have a 2 degree alcohol because there's 2 non-hydrogen things bound to this carbon, which is then bound to the alcohol group here, or the hydroxyl. So let's just look at a few of these reactions. So we're going to take an aldehyde here, very simple one, CH3, COH. It reacts with hydrogen gas, with palladium. Palladium acts as a catalyst. So remember, in our sense, catalysts help speed up a reaction, and catalysts help speed up a reaction in our case because it actually provides a surface for the gas and the aldehyde to interact on. That's all the catalysts are doing. But we're producing a 1 degree alcohol here. Just replacing this double bond with 2 hydrogen single bonds. Then we have a ketone here. It reacts with hydrogen gas on a surface of palladium, producing a 2nd degree alcohol. So nothing crazy, but reduction definitely a new thing for us. So let's look at a specific example of this. So we can use a reduction reaction to actually synthesize the prescription medication Prozac. This is actually how they do it in a laboratory setting at pharmaceutical companies. You guys probably know Prozac is used for, I was going to say the big sad. It's used for a variety of mental. My sister would punch me if I said that to her. Sorry, my sister's a psychologist, so she would hit me if I said the big sad to her. For like depression and anxiety disorders and stuff like that. Now we have our a multi-step reaction here. So you notice we have a reduction reaction here and a reduction reaction here. And the first thing we have is ketone. That's what we start off with. It's reduced, thus forming a second-degree alcohol. And then we have a subsequent reaction that basically takes this mess of a substance here and replaces it with a benzene ring, or as I say, tacks on a benzene ring here with a CF group here as well. So this is how we make Prozac chemically. So, in case you wanted to know, there's lots of cool examples of oxidation and reduction reactions in the world of biopharmaceuticals. Just as a note, if you're interested in that. Now, biological systems don't have hydrogen and palladium to use as agents. Does anybody know why that is? There's two parts here, right? Why don't we have hydrogen? Why don't we have palladium? And I say hydrogen as an H2. Does anybody know why? So it's being oxidized. That's an interesting way to think about it. So it's gone. It's not there because the hydrogen is usually being oxidized. That's one way. Yeah. So hydrogen gas that's present is usually oxidized pretty quickly. Anybody else? Does anybody know anything about palladium? So palladium is what we call a rare earth metal. So as its name implies, it's rare. So it's not too common. Palladium is also toxic. So microbes and anything else that would want to use it just simply couldn't because it's toxic. So that solves the palladium problem. Now, hydrogen gas is actually super duper rare. Hydrogen gas makes up 99% of the mass of our solar system, but it's actually just found mostly in the sun. Hydrogen gas actually cannot be captured, won't actually stay in our planet. It actually escapes right out of our atmosphere. So there's basically no hydrogen gas anywhere on the planet. That's not anything to do with chemistry. That's just a fun fact to go forward. Just figure out what you know. So, anyways, now biology uses an enzyme called coenzyme NADH. Now, for those of you guys that remember from Bio 1, or if you haven't taken Bio 1, NADH, nicotidamine, actually, I'm not going to try to say it because I'm really bad at saying that word. It's essentially a high energy electron carrier. It's really, really common in biological systems. It's involved in respiration and photosynthesis. Now, they use coenzyme NADH in this reaction. So they take our ketone or our aldehyde, they use this enzyme to make that first or second degree alcohol plus NADH. So in this case, NADH is oxidized to NADA. So we have a biological oxidizing agent. Now, in the previous examples, we have hydrogen as the oxidizing agent. So hydrogen is being oxidized while the ketone is being reduced. Yeah, that looks like you have a question. Just ask. Now, let's talk about cool applications of these things. I already talked about a few, but we'll talk about a few more. Yeah.
Does that mean that the H gas is in
Well, there's no H2 gas here, right? Yeah, so the NADH is oxidized. The carboxylic acid or the ketone is being reduced. So in the previous example, this is being reduced. This hydrogen gas that we've been using here is being oxidized. Now, human eyes are actually all eyes in general. It's not even just human eyes. Eyes are one of the most remarkable biological structures on the planet. They really are. Our eyes are among the best. They're not the best, but they're among the best. And eyes are crazy. You guys, if you're taking biology 2 with me, spend like 5 or 10 minutes like staring at the eyes of the grasshoppers we're going to dissect and the eyes of the fish we're going to dissect. They're remarkable. Eyes are crazy. But human eyes, which are equally as cool as frog eyes or fish eyes or grasshopper eyes, are consisting of two types of light-sensitive cells, the rod and the cone cells. You guys might have heard this. Now, the chemistry of vision in the rod cell centers around the aldehyde 11-cis-retinol. Retinol, you can tell that's the aldehyde. Cis, referring to the directionality, right, of the constitutional isomers, and the 11 part being, it's at carbon 11. So, fun facts. And you can look up what the ret part means. Now, in our case, the cis double bond is actually isomerized to the more stable trans. So just you cause it to flip on its axis, right? Remember, cis is on both sides, trans would be on opposite sides. Now, this process sends a nerve impulse to your brain, which is then converted to a visual image, which is crazy, right? This simple chemical reaction means I can see your faces. I can pick out this chair is red and gray and, well, sort of gray, it's like a whitish, but it's brown, right? It's crazy, right? Just a simple chemical reaction. So it's the same chemical reaction. Now, the question for someone that's visually impaired, there's many number of ways that can happen. Now, the most common way is you actually have a degeneration of your rods and cones, which prevents you from taking in more light. So part of this is the chemical reaction, which is usually going to occur. But the big part is taking in enough light and being able to process what that means, having the nerve cell. So the other problem is there can also be genetic disorders where you cannot actually physically do this reaction. So there can be genetic disorders where you just can't do this. So we can look at this. We have 11-cis-retinol. Again, the cis part is right here, right? They're both on the same sides, right? And where is our friend the ketone? So 11-cis-retinol in the presence of light. So light is what's doing it here. But remember, light has energy. Right? It's causing this reaction, which we call isomerization, which doesn't really matter that much what exactly is happening, but just know it's breaking cis into trans. Now, once it's in this, it allows us to have a nerve impulse. That nerve impulse sends an electrical signal, triggers the release of other neuro compounds, all the brain stuff, thus allowing you to perceive the light that comes in. Now, think about how fast that happens. Every second of every day, you have your eyes open, which is wild. This chemical reaction happens all the time. Now, for the process to physically continue, right, so you to continuously be able to see, right, this reaction has to be reversible. And you would be absolutely right, it is. So we actually have to convert all the trans retinol back to cis retinol. Now, this is done by a series of biological oxidation and reduction reactions. So the pairing of them together. All trans-retinol aldehydes is first reduced by an enzyme called, first reduced by NADH, which is just a compound. And all trans-retinol, to an all trans-retinol alcohol, vitamin A. So if you guys have ever heard vitamin A is good for your vision or carrots are good for your vision, see? Does it work one-to-one? No. But if you have a vitamin A deficiency, this is not going to happen too well. Pretty cool, right? Then all our trans retinol is then isomerized to 11-cis-retinol and then finally oxidized by NAD plus back to aldehydes 11-cis-retinol. Lost that. So this reaction allows us to do a lot of things. You don't need a lot of light for this to happen. So even if you're in a dark room, there's still light there. You might not realize it, but there's always little bits of light out there. Light is kind of cool. So it allows you to see at night pretty well. Not as well as, say, like cats, which have really big cones and stuff like that in their eyes, but you still have some low capacity of night vision. And again, it only requires a little light for this reaction to occur. Now, those that have a deficiency of vitamin A can, in their diet, can actually have what's called night blindness, which is just a condition that means you can't see at very low light conditions. So you probably shouldn't drive at night. I mean, some people just shouldn't drive at night at all, but that's not to do with vitamin A. Some people are just really bad drivers at night. Like my wife, she don't drive at night no more. She's not a good driver at night. So we can look at what this going on. We have the pupil, which let lights in. There we go. And then we have a cross section of the eye here. And what does this look like? Well, we have what's called a rod cell, very specialized looking cell, right? Those of you that know cellular biology, you know, the nucleus and the regular cell, we have this wild and wacky shape. No.
Good. I was going to ask what causes that sting organisms, but I can probably look that up. So.
I actually don't know the answer to that question. You definitely have to look that
Yeah,
up.
I'm just gonna look it up later.
I actually don't. Yeah.
Speaking about like the pupil and light from the pupil, you think it's possible if it would be dilated, like through I don't know, a drug and you know how cats they're able to see at night because their pupils dilated. Do you think it's possible for humans to be able to do that if they run the drug to see a lot better?
I think it depends on the drug. No, just kidding. So that's a good question. So the how much your pupil dilate is, i.e., how much the black part increases, the pupil increases, is essentially reflective of how much light is present. So when it's very dark out, you have much larger pupils because your eye is trying to get more light in so you can see. That's our primary mechanism of interacting with this world, right? When it's very bright out, so you stare directly in the sun, and you could do this. You could take your phone, look in a mirror, shine your phone on your eyes, and your pupil will just get real small because it's too much light. Now, cats and other organisms that have nocturnal vision have lots and lots and lots and lots of these rod and cone shells, significantly more than we do, because you need these cells to actually physically interpret the light. And one of the things they have is actually a protein called rhodopsin. Rhodopsin is a really wild protein. If you've never heard of rhodopsin, you should Google rhodopsin. It's really cool. But rhodopsin has essentially this, depending on the organism, but in our case, we have the 11-cis retinol part. Now, cats just have way more of this. Thus, they can process way less light. So think about like your sense of smell. Our sense of smell stinks. Why does our sense of smell stink? Our noses are tiny. We don't have a lot of surface area. Dogs, long snouts, fantastic senses. Much more neuroreceptors for smell. Same thing with cats. Much more of this going on than we do. Our vision is attuned differently than cats, right? Cats are nocturnal predators. We're not designed to be out at night. Same way we're not designed to be in the ocean. Without flippers. But anyway, so we can look at this sort of the cellular biology here in the cross-section of this eye here. We have rhodopsin, which has a protein that has our retinol in it. It catches the light, changes it, thus sending a signal to the optic nerve. Optic nerve heads to your brain, thus tells your brain, I see a cat, it's brown, it's all these things. Now, a couple things. Now we have all trans retinol. Now it can be reduced to vitamin A. Now we can get vitamin A from our diet. Now cis retinol, which is what we need for vision, can actually be derived from vitamin A. So we can isomerize vitamin A to 11-cis retinol and then oxidize that to cis retinol. So eating vitamin A is good for your vision, but not in the sense it's going to make you see better, right? No vitamin works that way. So eating lots of vitamin A is great because it helps your vision, but you're mostly just going to pee most of that vitamin A out. The same thing with vitamin C. Vitamin D, well, vitamin D you store in your fat and you poop out. But most vitamins, you eat too much of them, you just excrete them. They don't improve anything about you. So vitamin C is associated with a healthy immune system, but dosing yourself with vitamin C does nothing for your immune system if you're not at a deficit for vitamin C. The same thing here. But if you're not getting enough vitamin A, you should eat more vitamin A. All right, so that's all the body stuff I think I got. Maybe I have one more thing, but I think that's it. Now, aldehydes can actually undergo addition reactions with alcohols to form what we call hemiacetyls and acetyls. So this happens in the presence of sulfuric acid. So in this case, we have an aldehyde or a ketone. It reacts with an ROH just being an alcohol, in the presence of sulfuric acid. We first form a hemiacetyl, which is, you can sort of see the similarity in geometry right here, right? We broke this double bond to form an alcohol here. And then we have OR, which is essentially just replacing this, right? Or as an addition, you can think of it either. And then we can convert those with more alcohol and more acid into an acetyl, which is RCOR water. So this is another reaction that our aldehydes can undergo. Now, this addition of one molecule of an alcohol to an aldehyde is what we call a hemiacetal. Just mentioned that. And a hemiacetal then reacts with the second molecule of alcohol to form an acetal. So again, just what we saw. But one carbon is bound to an hydroxyl group, one is bound to an OR group, and then here one carbon is bound to two OR groups. So distinct. And remember, R can be, in the case of oxygen, it could be hydrogen or anything else. So let's use an example here. We have a very simple aldehyde. It reacts with ethanol in the presence of sulfuric acid. And you can see that we tack on essentially OCH3, CH2, right? This part here, and we were getting a hydrogen here as well. That produces our hemiacetal, and that hemiacetal can thus react even more with hydrogen sulfide sulfuric acid present, not hydrogen sulfide. Again, producing OCH2, CH3, again, two of the exact same groups coming off that center carbon. So we no longer have, really, we don't have an aldehyde at all anymore, right? We're producing these acetals, again, from our starting aldehyde. Now, we can also have cyclic hemiacetals that contain 5 or 6 member rings, and they're typically pretty stable. Now, we have hemiacetal general structure, right? COH, COR. Now, cyclic hemiacetals take a slightly different shape. Now, you guys have been seeing these. You just didn't have a terminology to define them yet. Right? We saw this one, a similar one to this one on your exam, right? It was a ketone. I'm not a ketone, an ester, right? But when we tack on a hydroxyl group here, it actually takes on a new life. So just as a note, you've seen a compound very similar to this thus far. So in this case, we can have cyclic hemiacetals. How does that work? Well, again, we have the OR, which would be OR here, and we have the OH, which is just the OH here. So acetals are formed by intermolecular reactions of a compound that contains a hydroxyl group and an aldehyde as well. So we can look at this. We have 5-hydroxypentanol. We have our aldehyde here, and we have our hydroxyl group at the end. So 5-hydroxypentanol. We haven't named this type of thing yet. You don't need to worry about this naming structure here at all. But we can redraw it in a cyclic version here, linking this, forming our hemiacetal. Just as a note, how we go from sort of this structure to this structure. That's what it looks like geometrically. Now, the most common and simple carbohydrate, glucose, is actually a cyclic hemiacetal. You guys might not have known that. Kind of a fun thing. But glucose, the basic sugar of all life, the most simple sugar out there, or one of the most simple sugars out there, is a hemiacetal. And again, if you've ever looked at the structure of glucose, you'll notice there's an oxygen in that 6-member ring. And there's this HOCH2 group as well. So, in case you didn't think acetals were good for anything, they're good for glucose. Now, cyclic hemiacetals can also be converted to cyclic acetals by a reaction with another alcohol. So, if we react our hemiacetal here with another alcohol, so in this case we have methanol, in the presence of sulfuric acid, again, very similar to what we saw earlier. We don't really place anything in the ring, but now we have OCH3. So we're replacing this O group with the CH2. Lactose, so for those of you that like milk, weirdos, I had a friend in high school, his family used to drink, as a family of 4, used to drink 8 gallons of milk a week, which means each person in his family drank 2 gallons of milk every week. They drank it with everything. And it was whole milk too. If you're gonna drink milk, you should probably drink the one that has the most flavor. But 8 gallons a week is so much milk. I'm sorry, I just saw the lactose part and I said, people who like milk are weird. And I say that not because you're weird, because of my friend that used to drink 2 gallons of milk And he still does. He's 34 and he still drinks 2 gallons of milk a week. He's gonna die someday of milk.
Is he bad? It doesn't know if he's healthy.
Say again?
Is he bigger? Like,
He's a little smaller than I am.
yeah.
Yeah, I don't know. He's just one of those people that can drink eat anything they want. Yeah, that's a lot of milk.
I used to love milk.
I used to never
I
like
think most, like, Hispanics drink a lot of milk.
Yeah, that's true.
Yeah, but then I realized as I got older that's not healthy. So I put my parents on almond milk when I was like 11.
The rest of you as an 11-year-old. Anyways, lactose, the main carbohydrate in milk. If any of you are lactose intolerant, well, you simply just can't handle this bad boy. But you'll notice this bad boy isn't too different from glucose. In fact, there's a couple extra hydroxyl groups here, as you can see, but the really only difference is glucose is just this ring right here, whereas lactose is 2 rings. Just at the middle. They're not different by very much, but different enough that you need a completely different enzyme to break down lactose versus break down glucose. Now, lactose in our friend milk is comprised of both cyclic hemiacetal and acyclic acetyl. So we have the hemiacetal here and the acetyl here. Now, we can do the opposite reaction, because I know you were on the edge of your seat thinking about that. It can be converted back to aldehydes and alcohols by hydrolysis. So we add water to them. You'll notice that hydrogen sulfuric acid is still required here, so a very strong acid. But instead of adding an alcohol, we're just adding a water. Remember, we were dehydrating them before. Now we're essentially hydrating. Right? We're adding water back to this. So we can convert our acetyl here back into an aldehyde or a ketone via water in the presence of sulfuric acid. Noticing we're producing ROH, so we're liberating an alcohol at the end of the day. And this is what this looks like chemically. We have our acetyl. We break these 2 bonds. It reacts with water and sulfuric acid, giving us our carbonyl group. So now we have a ketone. So in this case, it's 3-pentanone. And then we have 2 molecules of methanol, CH3OH, which is just methanol. And that is going to be the end of today. Because I'm sure you guys, very much like me, are tired of looking at the reactions of ketones with everything else. So if you guys have any questions with this, please bring them to class Wednesday or shoot me an email. But otherwise, I'll see you guys Wednesday.